Welcome back to Derivability. If you're new to the channel, thanks for dropping in. I hope you enjoy. Today we're going to be taking a look at rigid body motion in 3 dimensions. Okay, and Euler's equations. Okay, so we're going to start with some object in blue. As you can see there, rotating about some axis, denoted by the dashed line, has an angular velocity vector omega. Okay, and maybe it has its tip fixed at the origin. Doesn't have to, but there could be another point, maybe another fixed point. Okay, and we want to consider the equations of motion, sometimes called Euler's equations of motion. Okay, so we want to take the sum of the moments and basically see what the equivalent of like an F equals ma, or sum of moments equals I times alpha might be for such an occurrence. Okay. All right. Well, you probably know, if you've got to the point where you are in this video here, you probably know that the sum of moments is equal to the rate of change of angular momentum. Okay, so h means angular momentum here. M, it means the moments. Maybe you call it the torque on the object. Okay, now A here means either a fixed point in the body or the centroid. Okay, so you might imagine that the centroid of such a body, I'll call that G, center of mass, is right there. Okay, or if not, maybe there's some other point A, which needn't be the tip of the object, which is a fixed point. Okay. Okay, so it's either the fixed point or the centroid. The centroid doesn't have to be the fixed point. Okay, now if you have to have a rotating coordinate system, a rotating object, what we can do is we can separate out this normal time derivative, so-called, into the time derivative in this rotating frame plus omega cross the vector we're wanting to find the rate of change of. Okay, now the capital omega can be any axis of rotation at any rate, but it's going to be convenient for us to take this omega to be the rate at which the object itself is rotating. In other words, we're going to place ourselves in the same frame as the rotating object. So if we do that, then that capital omega merely becomes the lowercase omega here, which we mean to be the rate of rotation of the rigid body itself. Okay, now in order to take the derivatives or cross product that we intend to do here, we're going to need to know what the angular momentum vector of a rigid object actually is. Okay, so you may have caught my video on the 3-dimensional angular momentum of a rigid object, where we derived the formula for h sub x, h sub y, h sub z. So here we have those components, right? And just by way of reminder, okay, if you see something with the same double subscript here, like I sub xx, this is called a moment of inertia. Okay, you probably are familiar with that. Definitely a lot more common than the other sort. Okay, and the double subscript there is only for consistency with the others that we have to have double subscripts on. Sometimes you just call this I sub x, moment of inertia about the x-axis. Okay, now if you happen to see something with 2 differing subscripts, this is called a product of inertia. Okay, and you've probably learned about that as well. Okay, and so the moral of the story here is that ultimately what happens is that the angular momentum vector of a 3-dimensional rotating object doesn't always have to point in the same direction as, or be proportional to, the angular velocity vector, okay, which is kind of a new and weird thing if you're new to this sort of thing. Okay, all right, so those are the components. All right, so now what we need to do is we need to imagine the derivative of this in the rotating frame and later the cross product. Okay, now in the rotating frame, all right, what's going to happen is that if we place ourselves in the same frame as the rotating object, then these components of the moments of inertia are going to be constant, thank goodness. We don't have to take time derivatives of those. Okay, so when we take time derivatives, okay, and I will just use a dot notation here to stand for the rotating frame derivatives. Okay, then all we need to worry about are the time derivatives of the components of omega. Okay, the components of I are going to be constant, which really is, kind of a huge simplification. Okay, now what we can do is one more thing to make things a lot simpler, and that is we can choose the coordinate system XYZ that I'm referring to here. We can choose the coordinate system in the rotating frame, okay, which we've discussed. But not only that, but what we would like to do is we would like to choose that coordinate system so that these are the so-called principal axes. Okay. All right, now what that means is that they reflect a certain degree of symmetry, okay? But furthermore, the principal axes are those for which the products of inertia are all equal to 0. Okay, so in my symmetric top over here, in our present case, we don't have to be worried about this being an axisymmetric body. Okay, but wherever the origin of coordinates is in this body, okay, we've chosen some coordinates here, maybe something like x, y, and z, so that those are the principal axes. Okay, and even though, for instance, I have these subscripts written in opposite order, the order doesn't matter. So I sub xy is the same as I sub yx, and so forth. So when we do that, then what we get is we get these so-called off-diagonal terms, the so-called products of inertia equaling 0. All right, so these h dot expressions, or dh by dt in the rotating frame, are much simpler. Okay, in fact, sometimes when we get down to this point, we just use single subscripting for the moments of inertia. Okay, you'll see it both ways. Okay, all right, now that also greatly simplifies our cross product. All right, so that is omega cross h. Okay, so let's take a look at that next. Okay, so cross product we can figure using the usual determinant approach. Of course, not the only way. Okay, and before I proceed, I should remark that just to save a little notation here, the h in what we're talking about here, the angular momentum, is always about either some fixed point or centroid. Okay, the math works out the same. Now, if it's not a fixed point or a centroid, then things work out differently. Okay, all right. So if we execute this determinant here, let's see what we get. Okay, so you guys probably know how to do these determinants, so you can check that. Make sure I've done it correctly. Just check it for yourselves. Okay. Now, again, I've written the omegas components in a specific order here just to kind of keep things straight. But what you'll notice is that I've got, a pair of common factors that I can remove from each component there. So after I do that, what I'm going to have is I'm going to have a product of omega components along with a unit vector, and then times a difference in two of the principal axis moments of inertia. So for this first case, it's going to be an I sub z minus I sub y. Okay. All right, so now let's just put these all back together in our sum of moments formula. Okay, so simplifying just a little bit and putting our two parts together, the rate of change of angular momentum within the rotating frame, those are the terms that have the dots on them down here at the bottom, and then also from the omega cross h terms. Okay, so what we have now with this set of three equations, okay, these are called Euler's equations for rigid body rotation. Okay, very useful. Okay, now there is just a bit of a downside, but under the circumstances, it's not too much of a downside. And that is that we basically are talking about something that has happened at a kind of a freeze frame at just one single instant in this like a picture of a rotating object. Okay. All right. So these are not necessarily formulas that are valid as functions of time or that can be integrated, differentiated. Okay, we've kind of given that up for the relative simplicity of these formulas. Okay, now there are other ways of taking care of that, but this is not one of them. Okay, but if you're interested in, say, what you suspect are the maximum torques that would need to act on some object, from an engineering standpoint, wanting to keep everything like below a minimum, and otherwise being able to handle everything else, well, then these would still be very useful. Okay. Now there's lots more a person can do with rigid body rotations in 3 dimensions, but it can get kind of complicated. There's lots to it. All right, so we're not going to do it in one big swallow here. So I'm planning 1 or 2 more videos on this sort of thing in rigid body motion in 3 dimensions. Okay, not sure on the timeline, but hopefully you'll get to see at least one more relatively soon. Okay, well, thanks for hanging around here. Appreciate that. I hope you'll subscribe to the channel if you enjoy this content. Maybe check out a few of my other videos. And I will see you back here again sometime soon.